an issue. I always mention to my class at this point that one semester I had a girl sitting like right there, and in some point in class, I think it was when I went to turn off the camera, she looks back at the camera, and then my editorial process for like posting these videos amounts to I take the memory card out, I plug it in the card reader, and I upload to YouTube. That is the entire editorial process. And then it like automatically chooses thumbnails, and just so happened to choose this girl's face. And so like my typical view counts are like 50, except for that like one video, it's got like 600, you know? So turns out people are less interested in math as opposed to other things. Anyway, I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for the students. Just ask that you be glorified in what we do, that we'd all just understand a little more about your creation today, and that you be glorified, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me just spend the first couple minutes talking about the syllabus and stuff. Well, first of all, the syllabus is not edited, so sorry about that, but a minority of you actually read the syllabus anyway. The syllabus is kind of silly. The course planner, on the other hand, which I've given to you, I have spent considerable time editing, and that actually gives you pretty much everything you need for the course. Like that course planner tells you when, just a second here, I need to kind of resize or something. Take that, projector. So the course planner that I handed you, it has my tentative day-by-day plan for the course, right? In here, in terms of grading, I collect 5 missions, each one of which is worth 50 points. There are 2 tests, each of which is worth 250 points, and the final exam is 250 points. That's it. There's no electronic homework. I don't even have quizzes in here. So it's pretty cut and dried. That's what you have to do. So I've given you, I thought I heard something. So you need to spend considerable time and effort making sure you get these missions done correctly. I wouldn't say that they're easy. I wouldn't say that they're hard either. It's more kind of, it's less of a sprint, it's more of a marathon. The missions are lengthy, and they will take you time. So, okay, so this is before I get into all that, here's my schedule for this semester. I'm teaching 5 classes that I know of. Well, there's a 6th one online, which I found out about last week. But that's okay. Residentially, these are the classes I'm teaching. So I have office hours 9:10 to 10:30, like Monday, Wednesday, Friday. And my office is, oh no, it's not right here. There's one other classroom. If you go to the next classroom, it's like right here in the math department. It's in the back corner, formerly known as the Spranex. Some of you are old enough to know what I'm talking about. I guess you all are, but show of hands, who's had class with Dr. Sprano? Okay, so if you know, you know. Dr. Joseph. Where'd the rest of you guys? Oh, you maybe took my class, I don't know, but well, there's also Majeric. Who took Majeric? Okay, so yeah. Who took calculus not here? Okay. Oh, Schmidt, yes, I forget. I should know. I co-taught a course with him last semester, you know. But okay, so I also have office hours noon to 2, Monday, Wednesday, Friday. That's my plan for the moment. I'm currently in a waiting pattern, waiting to find out when Dr. Sprano is teaching something called Galois theory to a couple students. It just so happens one of those students, I'm hoping to have a weekly meeting on research. So that might change my schedule, but we'll find out. If that happens, then we'll talk about it. Obviously, you're here, so you know this is differential equations. I hope this is differential equations. It is the course I prepared to teach right now, so if it's not, that would be embarrassing, but it's happened. So I'm glad that we have this room. I love this room. This is an actual room to teach in. Look at these boards. They're just, they're just wonderful. But, I mean, they could be chalkboards. It could be better. Oh, yeah. You guys would prefer me to use chalkboards. Chalkboards slow me down about 30%. Like, I cannot lecture as fast on chalkboards. It slow me way down. Anyway, so, all right, so let me stop wasting time here. So that's my schedule.
Is that posted on Canvas?
No, this is www.supermath.info, which is my website. On Canvas, I have not actually posted a link to this, but if you just kind of like go to the link I went to, so like here, if I click on this course website here, see I'm clicking right there. I go clickety-click, like so. I sent you guys a link to this page. So if you just go to this page and like just delete the differential equations.html and takes you back to like the main page, my schedule's there. If you have any trouble finding it, just email me. I'm jcook4@liberty.edu. Also, please email me. Do not use Canvas messaging. It is horrible. It is worthless. Let me emphasize this again. Do not use Canvas messaging. Send emails like a human. Wait a minute. I assume you're humans. I don't really check for bots in my classes. So that hasn't really occurred to me until just now. Anyway, so this is the website for this course. And I collect things here for our reference, like the course planner, which I just gave you a copy of. Also the lecture notes. These are what I usually follow. I don't really use the textbook so much. Although my lecture notes, where did I learn differential equations? I learned differential equations from your textbook. I spent 3 weeks one summer working all the homework in it, right? And then I knew differential equations. But I'm past that. I don't teach out of the textbook. If I did, it would be awkward. So I teach from my notes. They're here. And there's like 200 plus pages of it. This is our book, all right? And I don't really teach directly from here either, truth be told, all right? I follow my heart. So, much like many of the convocation speakers this semester. Let's see here. So, yeah, and then this is important. Well, I guess it's important. You guys are here, though. So this is the differential equations YouTube playlist for you guys. As you can see, there are no videos posted here, as I can't post videos until I actually record them, and this is the first class after all. But I will post them here, and you can look at them later if you want to. If you need to miss class for some reason, this is how you find out what happened, all right? And I usually try to post them the same day most often. I don't really take points off if you miss class. I will try to start top hatting soon. But if you ever miss like the top hat code or something, it doesn't matter. What matters is that you check the box on this sheet. This is my primary attendance. Top hat's just supplementary. I'm required to top hat by the university, so I top hat. But in my heart, your attendance counts right here on paper because I believe in paper. So papers never let me down. Okay, so any questions before I continue my yammering? So missions, there are 5 missions, and I'm in the process of writing them. So I've only written one so far, all right? So one of the things, so if I click on that right here, you can see it. It's also posted in the announcement that I just made about an hour ago. It's posted there as well. And so here's like mission 1. This is the first thing I'm going to collect from you guys. And so it's got 7 pages. You need to print these out. I prefer you print them single-sided. And so what I've done is it's pretty simple. Here's the problem, like dy dx equals to x plus 1 squared. You're supposed to solve this problem and write the answer in this box. All right? You do not work these problems out on this page. If you do that, I will instruct the grader to give you negative partial credit for not following instructions. Everyone hear me? Do not work them out here, just the answers. All right, so we got that. Now there are exceptions to that where, like every so often I'll ask a derivation. Obviously I don't want you to write the answer to the derivation on the problem. I want you to write it later. So here's the problem statements, which we'll get into the math here really soon. And so there's a bunch of questions, right? Bunch of questions. But a lot of these are pretty simple. I got a lot of these from like a well-known textbook. I didn't make these up for the most part. So they're not going to be too horrible. When I make up problems by myself, they're worse, usually. But these are from textbooks, so by and large, they're not too bad. And some of these I've given in the past, so I know that they're not too bad. So you need to start working on this. You need to start chipping away at this. This is not something, I know it is a virtue in engineering to solve the homework the day before it's due. I understand that's like a rule of engineering students. It's the most virtuous form of achieving an assignment is to achieve it at the last possible moment because it's dangerous. And we all know that if you do something dangerous, it's courageous, right? Or something, I don't know. I'm not sure exactly. I understand it, but I try to discourage it here because doing that will make you only accomplish about 20% of the homework, which then will make you fail my test. It's just going to happen. Anyway, my point was at the end of this, for example, I have a problem here, which is this is like a derivation problem. And so this one, I don't expect you to write the answer right here. I expect you to write the answer in the sheets that you put after this. So what you're going to do is you're going to print this out. And then after this, you're going to write out the solutions to these problems. You write the solution, you box the answer in the solution sheets that you provide after this, and then you write that answer again in the box on the problem sheet which you have printed out. All right? You must print this out. You will find a way to print this out. I am not making you buy a textbook. I am, however, asking you to print this out. All right? I don't think that's too much to ask. So, all right. Again, this is posted in Canvas as well. If you have any trouble finding it, do email me. I will help you. The other thing I've done is tried to collect every last problem that I thought was interesting on the same material that Mission 1 covers. And that's what this is. This is practice problems for first order differential equations, which is what we're currently covering. And in here, you'll find 11 pages of problems. 11 pages of problems, nothing but problems. Problems and problems and problems. And some of those problems are the same as the problems that I have in your mission. So as a point of order, one of the things I've had trouble with some semesters is I can't think of a problem to solve, you know? So I've decided to put that problem to death by making this list of problems. So if I lack inspiration on which problem to write down, I'm just going to pick up my handy dandy problem sheet and pick one. If I happen to pick one that's in your homework, well, good. Everybody should get that one, right? So does that make sense?
So you reference this when you're creating exams?
No. I mean, would I reference this when I'm making exams? Not directly, perhaps, but this gives you a window into my mind. So, I mean, is it relevant? I mean, I guess it's relevant because I'm the one who makes the test. So I'm also the one who made this. So But this is not collected, and I'm not writing solutions to these. However, let me say that there are solutions posted. There are a lot of solutions posted. Look down here. So if you look, first of all, I have YouTube playlist from last semester, 2018, 2017, 2017, 2016, 2016. Each one of these is a list of 50, I don't know how many, 40, 50, whatever. No, probably not that many, 30-ish. No, it's more. See, my stupid camera, it cuts off after an hour, so I always have two videos, one for the first hour and then 15 minutes at the end. I will eventually buy a camera that can take one video for the whole class, but, whatever. Once my YouTube channel makes the big money, yeah.
Why don't you use Teams?
Why don't I use Teams? Why would I use Teams?
You can record on there.
How?
You can set up a camera meeting. Teams also, but it'll record for longer.
Ah. But not with that camera. See, with Teams, I would have to use this, and then, yeah.
You can set up an external camera.
Yeah, but I hate Teams. So there's that. I don't use Teams. That's actually a great question. So getting to that point, I don't use Teams. So thank you. That's actually very helpful. So if you miss class or something, suppose I don't know. You get bit by a scorpion in your writing hand. So you can't come to class because your hand is swollen up. Fine. Stay home. Watch the video. It's all good. A Chick-fil-A is opening near your parents' house. You need to go because you get year-long chicken. I understand. It's important. Go. Right? You will not lose points here unless you don't turn in the mission. That's what matters. Also, a point of order. The mission is due a week before it is collected. So the collection date is not the same as the due date. What this means is that everyone in here has extra time. I will not accept missions after the collection date. That is when they're collected. That is when they're collected. They're due a week before, so you all have extra time. All right, just so we're clear, I will not take late missions after the collection date. Yeah.
What happens if you miss the class when you're collecting it? Is it just automatic zero and you come later?
That needs to be a priority. It's important. You need to make sure it comes here and is turned in on that day. Yeah.
But you said the due date is a week before?
Yeah.
So we have to have it done the week before?
It's due a week before, but I'm going to collect it a week after.
Okay.
So Don't try to understand it, just accept it. So, no, I cannot take missions after the collection date because I post solutions. It's not fair to anyone. First, there's two things. Number one, it's not fair for me to post the solution and then allow you guys to turn it in when everybody else has worked hard without the solution, right? That's one thing. The other thing is, if I'm waiting for somebody to turn it in, then everybody else who's waiting for feedback is just waiting on this one person who hasn't turned in their homework. I don't think that's fair to the class either. So for this reason, I insist that it be collected on the collection day, and that's it. Now, if you have some kind of personal emergency or something, talk to me. I do make exceptions, but one of the ways I accept, so like, if you look at the course planner, I think what I said about that, because this question always gets asked, you know. Oops, wrong course planner. I'm teaching another class after this one, you know. I think what I said was if you fail to turn the mission in at the time indicated or before, then additional weight is to be given to your next test. So like if you missed mission 1, for example, and it was just unavoidable, you then would have 300 points to earn on test 1 as opposed to 250. So you could still get the points back on test 1. But I really would strongly urge you to turn in the mission and try to get the points there. That's a much easier way to get points, you know? Time pressure on a test is not as good a place to get points as at your leisure. You just have to work this out, and you have the added benefit of once you work all these problems out, you will do better on the test. It is just a fact. Students who do their homework, all of their homework, do better in the class. I don't have an educational study to back this up, but I do have 15 years or whatever. How long have I been teaching? When did I start teaching? I don't even know. It's been a while. I guess it's 20 years. I don't know. But people who do homework do better. Go figure. You know? And doing homework is not just doing it the day before. It is a process. You go to it, you try it, you get stuck, you sleep on it, you come back to it, you try it again, so forth. Now, that's probably not as true in this course as in others, because a lot of these problems you should just kind of work your way through. But all right, enough of my ranting. I guess that wasn't quite a rant. I was getting to a point here, which was that if you go down the webpage, you'll notice that, first of all, I have like my old NCSU webpage, whatever that is, and just some random stuff. But this is perhaps more interesting. If you like Nagel, Saff, and Snyder, which is a good book, it's a great book. I actually do have homework solved from Nagel, Saff, and Snyder, a previous edition, like the 4th edition. But you know what? The problems stay the same from edition to edition. So if you want to, there's tons of solved homework problems right here. You can look at these as well. There's lots of examples there. There's examples in my notes. These over here are my old handwritten notes that later gave birth to my typed notes that you guys have a copy of that I'll use as the text, basically. And then if you scroll past this, these are the same handwritten notes I was just talking about. But past all this, come on, keep going. I have old practice tests with solutions, quizzes I gave in 2012, some old tests and solutions. There's lots to be found here, okay? So if anything, you have too many examples, right? But any questions? Otherwise let me get started. Yeah.
On the text that you gave us, when it says text like 13 through 24, are those like from the book or from your class? It says text.
Yeah, that means my notes.
Okay.
Yeah, my lecture notes.
That's over there, right?
Yeah, it's this thing right here. If you look at the announcement, it's in Canvas also.
Okay.
If you look at the announcement from today, it's there. If I can find it. Where'd that thing go? Anyway, let me put this away. Any other questions? Yeah.
So you said on test 1, like if we don't turn in mission 1 or mission 2, we can make it up on that test?
Yeah.
Is the same thing applicable for the other missions and other tests, or just the first one?
Oh, everyone. Yeah. It's just I'm going to add points to the next test. So like mission 1 and 2, if you miss those, we would add weight to test 1. mission 3 and 4, we'd add weight to test 2. And when I say add weight to test 2, what I really mean is I'll take your score for test 2, divide by 5, and then put that number in mission 3 and mission 4. And then like the mission 5, we'll get that one from the final exam. But this is irrelevant. No one's going to miss any missions. Everyone's going to do the problems, right? So, yeah. Let me put this away. So in terms of the missions, you guys can work together, all right? But I would just remind you, like the point of doing the missions is not really to earn points. The point of doing the missions is to learn the material, right? So you need to do that for yourself. Nobody else can do it, right? I can explain the material to you, but I can't understand it for you. So those are different things. So let's talk about what is a differential equation. Anybody know? An equation with more than one variable. I guess that has to be true. So differential equation, which I would abbreviate like this, is an equation. This is going to be really deep, involving derivatives. All right. So this is exceedingly silly, right? But that's what a differential equation is. So for example, example 1, we could have something like dy dx equals to y. All right. Example 2, we could have something like y prime prime plus y equal to, oh, I don't know, t. All right. Example 3, we could have something like partial squared y partial x squared equals to partial squared y partial t squared. We have something like that. Those are partial derivatives. You guys have had calculus 3. You know what those mean, right? We could have something like, oh, I don't know, dr dt equals to, well, d squared r dt squared, let's say, equal to, like m times that is equal to big M g divided by r cubed r with a minus. These are all differential equations. Let me talk a little bit more about the terminology here. So like the first one, this is a first order linear differential equation. A differential equation is first order if it only involves first derivatives. This is linear because there is no, in fact, all of these differential equations are linear. To have a differential equation which is nonlinear, you'd have to have either the derivative or the dependent variable itself appearing in a nonlinear fashion. So like, to give you an example of a nonlinear one, we could have, for instance, dy dx equals to xy squared. This would be a nonlinear differential equation because of the y squared. Nonlinear differential equations are uglier. They're more subtle to solve, but linear differential equations have a very nice structure, as we'll see in this semester. So the second example here, example 2, what is that? Well, that's a second order differential equation because it involves a second derivative. We're going to be focused today on solving first order differential equations, right? Everything here, except for example 3, are called ordinary differential equations. So ODE equals ordinary differential, let me not write it out, differential equation. PDE equals partial differential equation. What's the difference between an ordinary and a partial differential equation? A ordinary differential equation only involves one independent variable and derivatives with respect to that one independent variable. A partial differential equation has more than one independent variable, and you see derivatives with respect to each of those variables. So like example 3 is a partial differential equation because I have a differentiation with respect to x and t, which are understood to be independent variables. Example 3 has a name. This is an example of a wave equation. This is the equation that you study if you want to understand like waves on a string. It's also second order, right? I'll teach you a little bit how to solve that at the very end of the course. We'll be able to do it. Now, each one of these is a single differential equation in the sense it's just one equation, right? However, example 4 is not actually one equation, right? That's actually a slick notation for 3 differential equations. This is actually a system of differential equations. See, because what we're looking at here, if you'll allow me the Newton's notation, this is mx double dot, my double dot, mz double dot equal to, all right, minus mmgx divided by x squared plus y squared plus z squared to the 3/2 power. That's what's going on there. R is the position vector, right? Physics 231 is a prerequisite for this class, so I take the gloves off with physics here from time to time. I'm probably never going to ask you to solve a free body diagram, right? But I will talk about energy. So this is like same but with what? Same with what? With z, right? So if you look at that, these are 3 second order differential equations, right? X double dot means x prime prime, or d squared x dt squared. This is Newton's notation for the time derivative. This is rather ugly. So here we have 3 second order differential equations which are coupled, meaning that they're intertwangled, aren't they? We actually never learn a technique to solve this in this course. So I'll just leave that for a later course, I guess. But it is nevertheless an interesting example because this is what? What's the force I've written on the right-hand side? This is what? This is Newton's second law with what? Gravity. Yeah, with gravity. So solutions to this are, of course, known. And you studied them in Physics 231. So let us now narrow our one other general concept, then I'll actually dive into the first order material. What does it mean to find a solution to a differential equation? Like, what would a solution to a differential equation look like? A function? It could be that, sure. And so like here, what's the solution to this one? Y equals to what? We could do y equals to e to the x, right? If I do y equals e to the x here, the derivative of e to the x is e to the x. How did I solve this differential equation? Educated guessing is the answer, right? I mean, the truth is I've done it before. But we know the exponential function, we know its derivative is itself, so that's a solution to this differential equation. This would be an example of this is a token solution if you like. The general solution here looks like the following. K e to the x. So it turns out that any possible solution to example 1 has that form for different choices of k. That's it. That's the only functions which solve this differential equation. So that's what we call the general solution. The general solution, it captures all possible contingencies. Right? If you're working for some employer and they say, I want a general solution to this problem we're facing, what that means in this context of language is that they want you to tell them how to respond to any possible contingency. That's what the general solution does in differential equations. It tells you every possible contingency. Now, let me pull from the thin blue air. The solution here is y equals to c1 cosine t plus c2 sine t plus t. This is actually the general solution to that problem. Now you might say, how did you know that? The answer, again, this is being very unsatisfying for you, is educated guessing. I can't really teach that to you as a method, right? Until you've had the course. At which point the question becomes, why am I teaching you the course again? Hopefully we don't have to ask that question. But, so anyway, if this is this really true? Plug it in. Differentiate twice. What happens when you twice differentiate cosine? You get minus sine, differentiate sine, cosine, right? So this goes back to minus itself. C2 sine t, when you differentiate it twice, it gets back to minus C2 sine t, right? Differentiate t 2 times, it's gone, right? So if you think about plugging this formula into the differential equation, search your heart. You should find it is true. So follow your heart. Believe me, this is in fact a solution. Now, why is that the general solution? That's something we'll talk about, right? So I think this is enough to illustrate the idea. Now, somebody said it's a function. So actually, both of these are examples of explicit solutions. And explicit, these are both explicit. Explicit means function. So explicit solutions means y equals stuff. All right. So that's a very vague definition, but I think it's going to work for us as long as we're talking about the dependent variable being y. So let's solve some problems. So great. That's just a quick backdrop into the terminology of differential equations in general, but now I'm going to turn the page here and start talking about techniques. First order differential equations. I want to talk to you guys about techniques to solve a first order differential equation. So the problem we face is this. We're trying to solve dy dx equals to some function of x and y. The goal is to find a function, right, that we can plug into the differential equation and solve it. Or as we'll soon see, we'll also have to sometimes be content with finding an equation whose differential consequence is that differential equation. All in good time. We'll see this in the examples. So, first example. Well, I guess it's technically example 5 for us. We want to solve dy dx equals to y. All right, this is a good place to start. You should all have seen this in like calculus 2. We cover differential equations in calculus 2. This should be old news. Yep.
That's example 1.
I know, right.
You said it's 5.
No, it is example 5, but this is a different one. Hang with me, you'll see. So we separate variables and we integrate, right? Separate, integrate. Integral of dy over y is natural log the absolute value of y is equal to x plus a constant. So here's the difference between example 1 and example 5. Example 1, I was just guessing. Example 5, I'm going to derive the solution for you. All right? So now that we've got to this, how do I... So like, point of order. If I was to stop right here, I could do that, put a box around it, and say solved. General solution. That's partly true, not entirely. It's almost true. So this is an implicit solution. I'll say it's an implicit, mostly general, mostly general solution. I'll explain what I mean in a second here. The reason I say it's mostly general is it's actually missing a case. Which case is it missing? Can you tell me? What's that? When it's not a constant? The opposite of that. How about when y is a constant? So what constant would solve this differential equation? You want dy dx equal to y. What's the derivative of any constant function? 0. So the 0 function solves it. Is the 0 function contained in the boxed equation? Certainly not. I can't put 0 into natural log, right? Try it in your calculator if you don't believe me, right? Proof by calculator. I sometimes dream of teaching a course with only wrong answers. To make the course complete, I would design a calculator that reinforced all my wrong answers. And I would give it to the students, and then they would plug it in their calculator, and it would give them the same wrong answer. Yes. I haven't had time to construct the course, though. It's one of my dreams. So instead, I just mostly focus on confusing the students I have. So it works. So this is, the reason this is not explicit is I have not solved for y, right? An explicit solution, we have to solve for y. How do you solve for y here? What do we do? Exponentiate the equation, right? E to the natural log, the absolute value of y, is equal to e to the x plus c. But you know these are inverse functions, so this gives us absolute value of y is equal to e to the c times e to the x, right? But what is absolute value of y? Absolute value of y is plus or minus y, right? So I can logically trade this for y is equal to plus or minus e to the c times e to the x. At the moment, it's still, this is I would say that that's an explicit, mostly general solution. Mostly general, because it's still missing the y equal to 0, right? Is e to the c ever 0? No, the exponential is positive. So this little, like taking this and labeling it as k, what happens right there, and this is kind of funny, if I just call this thing k, then I've got the general solution. See, because k, we just say, well, we allow k to be equal to 0. Logically, that doesn't follow from the step above, right? But it is permissible for the original differential equation, right? 0 does solve it. So putting k equals to 0 is a reasonable addition to the storyline given to us by separation of variables. Separation of variables sometimes misses a solution, right? Why? Why did it miss y equal to 0? What's the reason for that, logically? Do you guys know? Why is y equal to 0 lost in our mostly general solution? What step made me lose it? What can't you do if y is 0? We can integrate, but yes, divide. We can't divide by 0. This step right here is why y equal to 0 is an extraneous solution to this technique. I usually tell students that if I was a rapper, I'd be extraneous G, and my tagline would be, I'm not even in the solution set. So that lands much harder in college algebra for some reason. Here you guys are just worried about the mission at the moment, but you shouldn't be, because after you finish the mission, you'll be ready for the test. Probably. Okay, so example 1. So techniques, let's keep track. Number 1, separation. I can't spell. Let's fix this. Separation of variables. That is our first technique, right? Let's look at another problem. Example 6. Suppose you want to solve dy dx plus 2 over x times y equals to, oh, just a second. What am I doing? What I say at the start of class, I made these practice problems so I stay out of trouble. Un momento. Here we go. Let's make sure I work one that I can work. Let's try. Dy dx plus 3x squared y equals to x squared. This should work. That's from PP7. How do I solve this? So the first thing I would try would be separation of variables. So you guys try that. Is it going to work? Can we solve every first order differential equation with separation of variables? No, we really can't. Yeah, we really can't. So this one is one where we can't use separation of variables. So what we do here, and you should have seen this in Calc 2. If you didn't, I'm sorry, but we'll talk about it again here, is we'll use something called the integrating factor method. So step 2 is if you have dy dx plus py equals to q, then use integrating factor method, which we'll do over here. All right, so the integrating factor, I, is the exponential of the integral of 3x squared dx. All right. So, so show of hands, who has not seen the integrating factor method before? A few. All right, so let me derive the method while we're doing it to make it a little bit less mysterious. So this is a I would say it's kind of a trick. It's a technique. So here, I'm going to show you this works always. So we have got dy dx plus py equals to q. We're going to let I equal to the exponential of the integral of p dx. All right. The cool thing about doing that is when we differentiate, well, first of all, you can do this integral over here, right? What is the integral of 3x squared? Yeah, x to the third power, right? So that, I mean, I can't integrate p symbolically, but we can do the following. What is dy dx equal to? What's the derivative of the exponential of the integral p dx? How's that go? It's the exponential of the integral of p dx times the derivative of the integral of p dx, right? That's the chain rule, right? If I differentiate an exponential function, it's the exponential function of the inside function times the derivative of the inside function. Here the inside function is the integral of p dx. What's the derivative of an integral? Yeah, they cancel out. They're inverse, right? So the derivative of the integral is just p again. So this piece right here is p. Notice that this piece right here is I, so we just get ip. dy dx is ip. All right? Now here's the genius of the integrating factor method. It says that if you take your given differential equation, which is linear, all right? A linear differential equation is one which fits this pattern. So this right here is a linear first order ODE in so-called standard form. So you take that and you multiply by I. So let me call this star, make it famous. Multiply by I. That gives me I dy dx plus ip times y is equal to iq. But what is ip? We just had it up there, right? So I dy dx plus di dx times y is equal to iq. This is the brilliance of the integrating factor, is that it takes a term without a derivative, namely the py term, and it turns it into something that is a derivative. And it does it in such a way that these two terms get put together. This, by the reverse product rule, or just the product rule really, is d dx of I times y is iq. So lo and behold, we get that y is equal to 1 over I times the integral of iq dx. And that, my friends, is the general solution to the linear problem. Any linear first-order differential equation can be solved by calculating the integrating factor and then integrating the integrating factor times q and dividing by the integrating factor. Now, not only do I not advocate for you using the formula you can't see in the bottom of the board right now, I strongly advise you not to use this formula. This is, what I'm showing you is a way of life, a ninja way, if you will. So this is the way you should walk. You should follow these steps. You should try to replicate these steps for the example. All right? So we already did the first step. We calculated the integrating factor. The next step is to multiply by the integrating factor. So we have e to the x cubed dy dx plus 3x squared e to the x cubed y equals to x squared e to the x cubed. All right? We have now multiplied by the integrating factor. That's the next step in the integrating factor method. What next? Then, if we did it right, we can do the reverse product rule. So this right here is d dx of what? It is d dx of the integrating factor, e to the x cubed, times y. See that? Product rule. But once you have one of the sides of the differential equation is a total derivative, and the other side is a function, what can you do? How do you solve such a thing? Do what? Integrate both sides, right. So we just integrate with respect to x, right? So on the left-hand side, we've got e to the x cubed times y. On the right-hand side, we've got the integral of x squared e to the x cubed dx. What's that? You all have had Calc 2. You should be able to write this down. This is 1/3 e to the x cubed. Differentiate it. What happens? You bring down a 3x squared. That 3 cancels the third I put there and leaves us with an x squared. So if you differentiate what I just wrote down, we get back to what we were integrating, which means that my antiderivative is correct. You're like, well, how did you do that? Calculus 2. You're not going to write it out? No. Why would I do that? This is obvious. No, I'm just joking. If you if you want to show steps here, what is this? What am I doing? It's a u substitution, right? So plus a constant. So just let u equal x cubed. Then du is 3x squared dx. So your du, your x squared dx is actually 1/3 du. All right. Okay. So at this point, is this an explicit solution? Not quite yet, right? This is, at the moment, if I was to put a box around that, let me put a circle around it. So this blue circle thing right here, this would be an implicit general solution. Implicit general solution. All right? And if I want to find the explicit general solution, it's very simple. I just do solve for y. And I get y is equal to 1/3 plus a constant times e to the minus x cubed. So there you go. That's the explicit general solution. So to reiterate, if the problem is linear, we use the integrating factor method. The integrating factor method, in a nutshell, is this. Calculate the integrating factor, multiply by the integrating factor, reverse product rule, integrate both sides, be sure you add a constant right there, solve for y. Right? Let's look at another example. Aw, man. What if we were trying to solve example 7? dy dx equals to, I don't know, x cubed y squared. We could try to solve this thing, right? So which technique should we use? In the techniques we've talked about so far, there are really three, although one's not technically a technique. Like the three things I've talked about thus far are guessing, right? Guessing, separation of variables, and the integrating factor technique. But the integrating factor technique's off the table here because this is a nonlinear differential equation, right? And besides, we don't need it because we can do what? Separate. So we got ourselves dy over y squared equals x cubed dx, right? Did I say y squared? Let's make that a y to the 22. There you go. That's more exciting, right? Still nonlinear. And then this gives me integrate both sides. What do I got? So how many of you, so what is the integral of the left-hand side, though? This is point of order. What is it? Tell me. Some of you are thinking natural log of y to the 22. Don't say if you're that person. I don't want to know. Because it's very, very wrong. And I'm being stereotypical. I'm assuming that you guys are just like my last semester, like my class from last semester, right? And something like 20% of the students were engaging in this natural log integral thing, which hopefully was wishful thinking. So what would you say?
I was going to guess and say like log base 22 y or something.
No. This is easier than that. This is the integral of y to the minus 22 dy. So we use just power rule. You add 1, and you divide by it. Right? Plus a constant. I mean, that's the integral. Because if I differentiate this, I get that. If you have a power, you just use the power rule with the one exceptional case, which is the minus 1 power, right? That's the natural log case. Otherwise, it's just this. What's the integral of x cubed? Yeah, 1/4 x to the 4th. Okay, so there you go. That is a implicit general solution. Now, if I wanted to solve for y, I guess I could. Fine. Y to the minus 21 is equal to minus 21 times 1/4 x to the 4th minus a constant. And so then y apparently is equal to minus 21 times 1/4 x to the 4th minus a constant, all to the minus 1/21 power. There you go. That's the explicit general solution, which you could rewrite a few different ways, but that's ugly. All right. Example 8. It's time for me to add another technique. These techniques are not mutually exclusive. So this one I'm about to write, 2x dx plus 2y dy equals to 0. This is a different format for the differential equation than we've looked at so far, right? So let me just make a remark. So, remark. We can trade dy dx equals to f of x comma y for dy is equal to f of x comma y dx, or if you like, f of x comma y dx minus dy equals to 0. So this business right here, which I'm going to put a box around, and this business up here, if I say this is star, this is the Pfaffian form of star. And I really should say a Pfaffian form of star, because you could multiply it by minus 1. There's different ways you could manipulate it, So a Pfaffian form is just simply a differential equation written as a differential form. In Calculus 3, you guys did talk about differential forms. If you think about it, we learned how to integrate these things, didn't we? Remember, like integral p dx plus q dy over a curve? That was the line integral. Remember that? But we also learned, excuse me, how to take the total differential of a function. Do you remember that? What was the total differential of a function? Like, let me just jog your memory a bit. What's the total differential of, say, sine of x squared y? How did that work? We did what? If I call this thing g for the sake of discussion, the answer was partial g partial x dx plus partial g partial y dy. That's the total differential of g. All right? So, for that, my silly example, the total differential here would have been, like 2xy cosine of x squared y dy plus x squared cosine of x squared y. Did I say, I meant dx there. I'm an idiot. Dx, duh, dy. All right, so I'm using the chain rule both places to pull out the derivative of the inside function. Partial derivative of x squared y with respect to x is 2xy. The partial derivative of x squared y with respect to y is just x squared. This is the total differential of a function. So now I've reminded you, we've all talked about this before in Calculus 3. Can you undo the total differential up here? This is the total differential of what? I heard an x squared plus y squared. I like it. Correct. What's the solution to this differential equation? It is exactly x squared plus y squared equals to a constant. That's the solution. If we can rewrite a given differential equation as the total differential of a function of two variables, then the solution to that differential equation is simply the level curves of that function. Right? It's the solution set of the equation of a function. Different c gives me different solutions, right? These are what? No one knows? Someone here knows what x squared plus y squared equal to a constant is. Circle, right? Unless I'm a jerk and I'm like, oh, I didn't tell you c was -1, so it's nothing. Nothing at all, right? So as long as the constant's non-negative, you got something. If it's 0, you get the origin. Otherwise, you get a circle of radius square root of c. So this is the third method of solving differential equations, which is that if you're given m dx plus n dy equals to 0, and you can rewrite this as the differential of a function equals to 0, then that implies that function equals to a constant. These are your solutions. Yeah.
Is that implicit?
Yeah, this is an implicit general solution.
So really to get explicit, you're just solving for y.
That's right. That's all explicit means. Solve for y if you can. But I really like to allow the concept of solution to not just be function. We don't want it to just be function. That is far too limiting. All right? It's far too limiting. Let's see here. So can you always do this? Is every differential equation exact? So if this is possible, we say such a differential equation is a quote-unquote exact equation. And we'll talk more about this in future days. But if this is possible, m dx plus n dy equals to 0 is an exact equation. All right. I'll talk more about the theory of this probably like next Tuesday.